And hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Matteo Cantiello with us today. Hey, Matteo.
Hey, Frank. Good to see you.
Good to see you. How are you doing?
Pretty good. Sunny day in New York. I'm at the office at the Flatiron Institute.
Okay.
And chatting to you. So that's all good.
Yeah, on this May 27th, my Thursday, it's a blue sky day in Phoenix. We'll probably hit in 35°C or so today. So the power switch hasn't really been hit yet. So give it another week or so and it'll start to toast. So it'll be great. So Flatiron looks sort of empty there. Are they allowing people back in at will, or?
It's, we are back and we've been coming to the office on and off and at reduced capacity for quite some time, honestly, since the last summer. And yeah, I mean, it's getting busier and busier. There are certain days where are busier than others, but it's nice. You know, we are able to have lunch all together on the 11th floor. We have a rooftop we can go to. Yeah, so it feels like things are slowly getting back to normal. Yeah.
Very good. Very good. Yeah, we'll start full in-person at Arizona State in August when we fire back up for the fall semester. So yeah, things are looking a lot better than they were. So that's a good thing.
Yeah.
So Matteo, what do you like to do for research?
I work on theoretical astrophysics and mostly interested in the role that stars play in a cosmological context. So really everything that happens inside stars and how stars work as building blocks for everything out there. So yeah, really, I'm interested in stars, and I've been diving deep into internal processes. I work on astroseismology. I work on fluid dynamics and simulations of stellar interiors. I'm interested in magnetic fields in stars. And, during the last maybe 10 years, I spent between low mass and massive stars. But definitely, I've been spending more time and put more attention in trying to understand the fate of massive stars, the one that make bright explosions, can be seen from afar, and more recently, the one that we believe create those interesting compact remnants that merge in LIGO bands. So everybody's excited about it. So that definitely pushed us to think more about those. And yeah, and more recently, been thinking about more exotic ways to evolve stars in very unconventional places in the universe. And I think that's what we're going to talk a little bit more today.
Indeed. That will bring us right to it. And we're going to discuss this very lovely open access APJ article on stellar evolution in AGN disks. And Matteo, take us away.
Yeah, so just want to say that this project, which I'm very excited about because it's starting a little bit of a new direction of research for me and some of my collaborators, and most importantly, allowed me to start thinking about astrophysical environments that I didn't know much about. And these are like the inner regions of galaxies where supermassive black holes are at work and are creating gas at high rates, and a disk is formed. It's called an AGN disk. AGN stands for active galactic nuclei. Really, I didn't know much about this astrophysical environments until maybe 2 years ago, and this is all new for me, but very exciting. And so how this came about, I want to mention that this project started after a discussion I had with Doug Glynn at KITP during a KITP program more than 2 years ago now, maybe even 2.5, 3, I kind of forgot. But and that project remained a little bit of an idea. We did some work initially, but then it got revamped here at the CCA, at the Flatiron Institute, thanks to Adam Germain, who joined the CCA and started working with me on this idea, and with Doug. We made a lot of progress together. So really, this was an approach and a project that really was advanced by all three co-authors. And we brought in different expertise. Doug definitely has a huge experience in all sorts of things astrophysics, but in particular, he knew a lot about accretion disks, and he knew a lot about the observations that challenge our understanding of this interesting astrophysical environment. And one piece of the puzzle that we were trying to initially understand was why AGN disks are chemically enriched almost at all redshifts. And it's observationally, it seems like if you look at the composition AGN disks, you find metals. So the metallicity tends to be high almost at every redshift you observe. So that points to a process that can increase the metal content of this of the gas very rapidly. Okay. What that is, people don't know. There are some ideas around, and we propose an idea in this paper that has to do with stars, and we'll get to that in a second. The other obvious application of what I'm going to talk about is in the context of production of massive star and compact remnants in AGN disks, something that people have talked about in the past in order to explain some of the peculiarities in the observation of the properties of mergers in LIGO. So what's the idea here? The idea is that the inner regions of galaxies have this 1 to 10% of galaxies in the universe are actually AGNs. So these things are fairly common, and the disk of these AGNs can fragment, so can undergo gravitational instabilities and fragment and form stars in certain parts of the disk. That's one option. So stars in AGN disk are things that have been thought about. The other way that you can bring stars into an AGN disk is by trapping. This is a process where a star which is nearby the AGN disk, and I'll tell you in a second why we expect that to be the case, can be captured by the disk by the very fact that orbital energy is dissipated by excitation of bending waves, and so in general by the torque exerted by the disk, which can, if the star is very close to the inner regions, can bring the star in the disk quite rapidly. Where quite rapidly here means in a short time compared to the lifetime of the AGN disk itself, which is discussed to be of the order of 1 to 100 million years. We don't know exactly how long those things live, but in the literature, these are like the number that are usually discussed. Okay. So why would you expect to be a lot of stars around an AGN disk? Well, we do see a lot of stars around the central region of galaxies, around the supermassive black holes. A number that honestly, really I was completely unaware of is that there are about 10 to the 7 stars within 1 parsec of the central of the Milky Way, or central region of the Milky Way. So around the Sagittarius A star, there are 10 million stars in about in the 1 parsec inner region. So that's an extremely high density of stars. And the stars are part of what is called a nuclear star clusters. There is a huge literature about these things. A lot of people, very smart people, have been working on observing and understanding these regions. And so if a disk forms, some of the stars are going to be naturally embedded in the disk, and some will probably be captured to this trapping process. And then, there is also the opportunity that some part of the disk will fragment and form star. So stars in AGN disk, I believe it's something that we expect astrophysically. And so the question is, what happens to a star in an AGN disk? Because we think about stars as usually evolving in the interstellar medium, which is a very low density, low temperature environment. For almost all purposes, the interstellar medium is a vacuum when you simulate a star with MESA or any stellar evolution code. The boundary condition assume that like the outside of the star has negligible temperature and negligible pressure, and so the boundary conditions are arranged that way. But in an AGN disk, that's not necessarily true. So if we move down to figure 1, which is kind of summing up like what I was saying about the picture of stars ending up in AGN disk or being formed there. This figure is also giving away a little bit something I'll discuss in a second, which is that stars that are either captured or formed in a disk become massive. So the yellow and the blue massive and supermassive stars are stars that are the outcome of the evolution of stars in AGN disk. Some we call them AGN stars. And here we also show that compact remnants are expected in the disk as the outcome of the evolution of these stars that grew up in mass. And how they grew up in mass, I'm going to discuss in a second, but as you can imagine, because those disks have high density, those AGN disks have fairly large densities, order of 10 to the 10 to 10 to the 14, density larger than the typical ISM densities. Accretion has to be an important process, and depending on the region of the AGN disk you are in, that can lead to a growth of the star in terms of mass that is competitive in terms of its evolution. So if you grow in the star more rapidly than you evolve it, then the star is going to change its nature. So you can park a sun in the AGN disk, and if the region is like dense enough, you're going to turn it into a 100 solar mass star. So that's the beauty of what's happening here, or the interesting part, if you want.
Yeah, definitely. Wow.
Yeah, so in order to understand the condition in the disk, obviously it's a complicated endeavor. People, have spent a lot of time trying to understand what's the solution that can describe the property of the AGN disk, and it's not an easy thing to do. In this paper, we sum up some of these efforts and show up some scaling relation that can lead to estimating what the typical density and temperature and sound speeds might be. That's section 3. I'm not going to go too much into the details of that. There's a lot of literature around it. There's also a lot of uncertainties. And what I want to say is that the existing AGN disk models out there mostly assume that the object and the stars that we're going to talk about that we're talking about in this paper do not exist. So a next step of trying to understand better this process is also including the feedback from the existence of these grown-up stars, like increased mass star, top-heavy population in terms of mass of stars to the disk itself. The important point of what I wanted to remember about this is that if you go at the end of section 3, we mentioned what a typical condition should be around some of these stars. And if you keep going, you will see that, I think it's at the end of 3.2. Yeah, so you see that the values of temperature, density, and sound speeds vary by some order of magnitude, but they tend to be high in all cases. And in particular, the density, the typical density can be fairly high. In fact, can be higher than what we reported here. You can have densities up to 10 to the minus 10 in AGN, in the very inner regions of AGN disks. What we're going to do, what we did in this paper is that we try to understand the evolution of a star embedded in a box, and that box will have specific value of the density, temperature, and sound speed, which we believe are relevant for some parts of the AGN disk itself. Okay. So it's a local simulation of a AGN star, and obviously, as you can imagine, there will be complication, and we can discuss a little bit of those at the end. But we don't include things like migration of the star. We don't include in this paper discussion of how the structure of the AGN disk and the presence of the supermassive black hole might impact the evolution of the star itself, in terms of how the supermassive black hole might prevent some of the material to accrete on the star, because instead it's falling into the AGN, into the supermassive black hole. But we did this in a follow-up paper with Alex Dittman and Adam Germain, which I'm not going to talk about, but this was the initial step. Okay, so the important things that we did, I think, in this paper is really trying to create a framework to study the evolution of these objects. To do that, we had to come up with some modification to the usual way we evolve stars. And the first important thing is really accretion. And as we discussed, we are in a high density environment. And so you could imagine that the star, which has a substantial mass, will start accreting at some rate. The first estimate for that rate is the Bondi accretion rate. Yeah. And that depends on the density of the AGN and the sound speed. Mm-hmm. So material will fall into the star from the Bondi radius. The Bondi radius is defined in equation 14. It's an efficiency factor for the accretion rate. Here we fix it to 1. But as I mentioned, we discussed a little bit more the accretion rate in a more AGN-like environment, a proper AGN-like environment in follow-up papers. The important thing here is that the accretion rate depends on the mass square of the star. So it's a little bit of a runaway process. If you substitute the Bondi radius there, that's what you get. Uh-huh. And so if your accretion rate is initially large, you can imagine this process running away, and that's why you make massive stars, or very massive stars. Now, so what happens if you accrete at this high rate? In this paper, we start with 1 solar mass stars, and for high enough value of the density and low enough value of the sound speed, we get to build stars that are massive. And by doing that, now we also have to account for other effects, for example, the effect of mass loss. And this is because stars that become very massive, they approach the Eddington limit, and we believe that, so this is the Eddington limit in equation 15, and as they reach the Eddington limit, we believe that they're going to start losing mass. So there's going to be this interesting process where the star is accreting, but at the same time wants to lose mass because it's so luminous. Right. Now, obviously, this is a complicated thing to simulate, especially in one dimension. The models that we evolve are one-dimensional. This process is likely multidimensional. There's going to be probably channels of material that wants to escape the star, and channels of material where material fall in. We came up with a way to parameterize this, and in a simplified way, where we assume that as the star reaches the Eddington limit, it slowly stops its accretion. So the accretion decreases incrementally until when the star is above the Eddington limit, the star cannot accrete anymore, and material can at that point be efficiently removed from the star. Okay. So I think that's in equation 16 or below. Uh-huh. Uh-huh. It's equation 16. Yes, that's how the mass flows work. And then we have an interplay between accretion mass flows, which are described in 4.3. Okay, so this is about accretion and mass flows, but I haven't yet explained another an important part of this, which is how do we implement the boundary conditions. As I mentioned, there is an accretion stream coming onto the star. And so this is a complex hydrodynamic problem where you can imagine as the star grows in mass, there is like this accretion stream hitting on the surface of the star. What was the surface of the star? And we're trying to understand how the star is going to react to that. Now, this is something that it's very complicated, but we can still simulate this using a solution code like MESA by giving the appropriate boundary condition at the location of the shock, which is produced by this accretion stream. So MESA wants to know the value of the pressure and the temperature at the location of this shock. And everything that is above doesn't really care about. As long as we give like MESA the ability to create a structure below the shock that is fulfilling the stellar structure equation, then we're good. So how do we know the value of the pressure and temperature that we need to implement? Well, the way we did this is by solving analytical equation that tell us a scaling relation for the quantities in the accretion stream. And so that's going to be actually discussed in, I think, section, yes, you're there, surface boundary condition, exactly. So here we give like the assumption and approximation that we take in order to come up with this scaling relation that we then use to determine the important properties at the stellar surface, which in this case is not the stellar surface that people usually think about, is the stellar surface of the MESA model. So it's in a sense, it's the outer grid point of the stellar structure in the MESA calculation.
Okay.
It's not necessarily what you would see if you were looking at the star from afar, but it's all you need in order to calculate the properties of the object, which is below the shock where the material is accreting. Obviously, if the accretion stream is optically thick, we won't see the surface, the shock. You will see something outer in the stellar envelope, or whatever you want to call this accretion stream entering, eating the star.
Yep.
Yeah. Anyway, so if we go down to equation 4. Equation 37. Equation 37 is showing the value of the pressure that we enforce at the surface, where again the surface is the surface of the MESA model, and this contains various terms. One is the typical usual adding to atmospheric conditions. So if there was no accretion stream, it would be just the first and the last term. And then you have two terms that have to do with the inflow and outflow. So there's a ram pressure terms that enter the equation for the boundary condition. There's also a term for the extra luminosity coming from the accretion stream. And then we also count for the extra temperature that is coming from the fact that you're heating the star due to this inflow of material.
Right.
So all this is implemented in MESA, as I mentioned, and we, thanks to the versatility of this software instrument, we were able to implement this extra equation in a Rundstar Extras file and allow the MESA to be able to calculate evolution in this strange type of objects. Cool. We made sure that if you reduce your accretion rate to be very low, or if you reduce your density to the density of the ISM, you still recover your traditional stellar evolution, which is something, if you did a good job, that should be the case. And then we went on studying what happened. The only other piece of physics that we had to implement is the physics of mixing. And this is something that I want to talk a little bit about because it's fairly important for the type of evolution we're going to see here. As I mentioned, if the star accretes a lot of mass and becomes massive, a couple of things happen. The star will become radiation dominated. And when a star is radiation dominated, it becomes marginally stable. So it becomes close to a gamma equal 4/3 polytrope. And as such, two things usually happen. First, its convective core becomes very large. This is due to the star is very hot in its core as well. And usually, for example, a 100 solar mass star is pretty much 90% convective. There's only a small relative layer in terms of mass. And so the question is, how stable is this relative layer? Yeah. Well, this relative layer is fairly unstable in the sense that it's close to marginal stability, but any type of instability can be activated very easily because the star is so close to the Eddington limit. And we believe that here the stars will very likely be mixed even in this layer because, well, the stars are going to be likely rotating, something that we don't discuss too much in this paper, what we discussed in a follow-up paper led by Adam Germain. And also, those stars are going to be affected by this constant accretion and mass loss process that occur when the star becomes more massive, as we discussed, which leads to the creation of circulations in the other region. Because, some part of the star are going to lose material and other parts will try to create material. And so, horizontally, at the surface, you're creating some kind of circulation and stream that probably helps mixing the star. So we're pretty confident that if those stars exist, I'm going to be fairly well mixed. And if they're very well mixed, means that they're going to evolve chemically homogeneously, which is a type of evolution where you constantly mix the core of the star with its surface, if you want. So everything that you see at the surface is a direct probe of the type of burning that is occurring in the core. It's an important point because allows the material that is lost to be enriched by a CO product, for example, material that has been burned before.
Yep.
So that's something we'll get back to in shortly. So let's move to some of the results. Now that I laid the foundation, we can move a little bit more rapidly into showing a little bit what these things look like, what kind of evolution we can see in MESA. Like figure 6 shows a little bit this point about mixing. Maybe I can show that before we go to that. In figure 6, we show how this diffusivity, extra-diffusivity that we implemented is allowing the model, as they grow, to start mixing its interior. So what we're showing here is the keep it unplocked. The surface of the star is the black line. The green hatched regions are convective. So you can see that as the star becomes more and more massive, its convective core becomes a large fraction of the whole star. Right. And there is still a radiative region, but in that radiative region, you can see that there is the diffusivity. So this is the extra diffusivity that we implemented to account for this ability of the star to be well mixed. And this diffusion depends on the luminosity of the star or its proximity to the Eddington limit. And you can see that at some point this diffusivity becomes large. It's already large in the convective region because convection is very efficient at mixing things. But around, when the star is reaching like 67 million years of age, you can see in the bottom panel, you start to see this flow of helium moving from the core to the surface. And this is a signature of the star now becoming chemically homogeneous. So the surface reflects the composition of the core. Okay, so I want to move back to figure 3. Sorry, there's a little bit of back and forth, but I feel like this was the right way to present this. Figure 3 is showing, again, a Kippenham plot of a typical AGN star at a density of 10 to the minus 18 or so gram per cubic centimeter. And this is one of these models that start as a 1 solar mass star and fairly rapidly create larger amount of material and reach about 180 solar masses. So this becomes a very massive object. But then the star is also able to evolve past the main sequence and get to helium burning. And as it does this, increases its luminosity and it starts losing material at a high rate. So this star enters a phase of large amount of mass loss driven by these super Eddington winds and end up as a Wolf-Rayet star, chemically homogeneous Wolf-Rayet star, not too similar from the models that people discuss for long gamma burst. And it ends up as a 10-ish solid mass model when it's burning oxygen in its core. The point we stop the calculation, we know that this object is gonna likely turn into a black hole when core collapse. And so we will expect this object to make a black hole. Now, if you don't get excited by 1 solar mass model making a 10 solar mass black hole, then I cannot help you. But this is the type of evolution that this AGN star can go through.
Very nice.
So that's why we got a little bit more interested and we ran a grid to see, where in the parameter space this will happen. And this is summarized in figure 8 and 9. These are like showing a grid of models run at different densities for constant sound speed. These are pretty dense plots in the sense that there's a lot of things going on here. So the top left plot is a log of the stellar mass as function of log time. And it shows the point that we have 3 types of evolution happening.
Okay.
One is like at low density. And you can see that at low density, not much happened. In fact, for very low density, we recover canonical evolution, which is, a 1 solar mass model stays a 1 solar mass model, lives for more than 1 billion years. And, that's our sun. And then if you increase the density, you enter this regime where the star actually can run away and become like a massive star. But it has enough time, so the accretion timescale is not much shorter than the evolutionary timescale. So the star is able to evolve to burn helium, becomes more luminous, and stays compact and lose a lot of mass through this super Eddington winds. They all ends up as 10 solar mass compact objects, more or less. These are like the star symbol.
Right.
Then there is this interesting feature of this type of evolution that is if you feed the star mass at a much higher rate that it can burn it, then you pretty much stall the evolution of the star. So the star is being fed fuel faster than it can burn it, reaches a point where now, okay, it stays at a fixed mass, and it's a very high mass, about 1,000 solar masses in this case, because at some point this super Eddington wind kick in and they balance the same amount of mass which is accreted is mixed inside the star, but is also lost. But the star doesn't evolve; it's immortal for all purposes.
Yeah.
You can have a 1,000 solar mass star living for 1 billion years, which is a crazy thing in stellar physics. You never see that because they burn so bright. They're so luminous that usually they burn their fuel very rapidly. So usually a star like this will live for 2 million years. But here it can extend its life as long as you want. Obviously, this is academic in a sense because those AGN disks are not living this long. We know that. And also we will expect probably the local condition of the disk to fluctuate in a way that, it will be very hard to feed the star at the same rate and high enough to prevent the star from rapidly evolving and turning to, this intermediate regime where the star will evolve rapidly away and lose its mass. But, that's interesting to see, there's ability to extend the life, rejuvenate those massive stars. The other plots just show the evolution in the core, so core density and temperature. You can see that the different evolutionary path, toward normal evolution, increased mass, massive star, and then the stalled star that don't make it to helium burning down here. That's interesting. And then we have HR diagrams, which I'm not going to discuss now. We don't have much time to do that. I just want to move to some of the implications and interesting future perspective in the interest of time. But This HR diagram just reflect the two ways to look at the star, either at the shock radius, which is showing to the right. So remember, this is the radius that Mesa knows about. And this, you can see here, there's a dichotomy in the chart diagram where you have normal evolution and star that move to the blue, very similar to what chemically homogeneous stars do. They turn into Wolf-Rayet stars, and you can see it there. And then the left plot is just showing what actually a star would look like in the chart diagram if an observer was sitting at the Bondi radius.
Ooh. So
looking down into the star. And in the left, you see that what's happening is that stars actually, as the accretion rate increases, there is a blanket on top of the star, which is your accretion stream. And given an assumption for the opacity in the accretion stream, which is also complicated, but in this case, we just assume electron scattering, then at some point you start seeing in the boundary of the star, it's in the accretion stream. So the star becomes a little bigger in terms of radius, and so its surface temperature, effective temperature decreases. So that's just to show that effect. And for all purposes, it would be very hard to observe these stars anyway because they're embedded in an AGN disk.
Sure.
So the question about why we haven't seen them, it's a good one, but I think there are some extra difficulties in observing the light coming from these things. Also because the AGN disk is extremely bright itself due to the fact that it's powered by accretion on a supermassive black hole, which is providing a large amount of luminosities.
Yep.
Okay. I want to show figure 13 because figure 13 shows the yields for the model that we discussed before. The one we showed the Kippenan plot for, and it's showing the amount of mass that is ejected into the AGN disk by this model. So this is the cumulative yield corresponding to the mass loss by the intermediate accretion model, the one which we had to look before. And you can see that there's a large amount of helium, as discussed, that makes it to the disk, but also interesting amount of CNO processed material, so a large amount of carbon and oxygen. And we expect a potentially large population of these stars to occur in an AGN disk.
Okay.
And this is also not considering the fact that some of these stars might explode, and there might be some supernova nucleosynthesis going on, and the ability to further pollute the disk. This is something we haven't really addressed in this paper. We focus just on the yields coming from the evolution during the life of the star.
Okay.
But the notion here is that it's possibly easy to pollute the disk with the material processed by the stars, these massive stars, and that can be done. And so this process might explain or be part of the explanation for why AGN disks seem to have high metallicity are all redshift. Because if this process is relevant, this can happen very rapidly. The stars can become massive on short time scale, evolve fairly rapidly, and pollute the disk on rapid time scales.
I just make a comment. It looks like the N14 is almost certainly coming from the CNO cycle because everything piles up at N14. But then it looks like you've also got some helium burning going on, triple alpha and then C12 alpha gamma, which is where this carbon and oxygen is enhancing from. So very nice. Yeah,
exactly. Yeah, you are the expert on nucleosynthesis, so I was expecting you noticing this. And yeah, absolutely. So this is a signature of the fact that the cores of these things are very, very hot.
Yeah.
Which usually you don't have in typical low mass or intermediate mass stars. So I wanna say a few things about why I believe this is interesting, important, and why I believe that there is a lot of potentially interesting avenue to test some of these ideas. So I'll start on the talking about the fact that this type of evolution can not only pollute the disk, but also lead to the formation of compact remnants. This is something, that people have discussed, the ability of forming neutron stars and black holes in AGN disk.
Right.
There's a lot of literature about what will happen to these compact remnants in the disk. They can actually migrate and then find each other and merge, and you can actually have multiple generations of these mergers. So maybe this is a way to explain the existence or the discussed possibility of having compact remnants observing the LIGO band that seems to avoid the parent stability gap, or sorry, that they're found within the parent stability gap, which is something that it's hard to do with single stars, or at least even in binary system, but with first generation mergers, something you will work on as well. And so here the idea is that, if these things are common in these disks and they migrate and they pair and they merge and they form multiple generation, then it's easy to to add to the mass and form things that are more massive. And so this is definitely something interesting, as in a sense, to provide the seed for those type of calculation. So knowing how many of these objects might be in an AGN disk, and maybe in what part of the AGN disk they initially form, so where they start migrating. There's a lot of interest in that direction, I think, although obviously there's a lot of physics happening between the AGN star formation or trap to the merger of the compact remnants as observed in LIGO, because the AGN disk is a complicated place. And so that's something that the beauty of it is that it requires a lot of different astrophysical expertises, from dynamics to stellar evolution to accretion processes. And I think that there is an argument to be made about bringing more people to think about this interesting astrophysical environment. And that's, I think, my motivation for diving a little bit more into this and starting collaborating with a number of very smart people. Some are mentioned in the acknowledgements that you nicely put up here. But the other interesting application, or at least place to look at for verification, or at least to understand if this type of evolution or this type of stars do actually exist, it's actually the galactic center. In the galactic center, there is no AGN right now, but people believe that maybe we had one, maybe 6 to 8 million years ago. This is potentially, a possible signature of this is seen in the Fermi bubbles, which are these interesting symmetric bubbles of high energetic energy emission above below the galactic plane. These are consistent with have been blown a few million years ago by some energetic process occurring in the center of the galaxy. Today, when we look at the inner region of the galactic center, and a lot of people have done this for a number of years. In fact, the Nobel Prize was won very recently for that work. So we have a lot of data about the stellar population in the AGN, around the supermassive black hole that is called Sagittarius A star. And there are a lot of anomalies that I wasn't aware of, and I learned only recently, in the last couple of years again. And it's very interesting. There is a top-heavy, so the stars actually in the inner parsecs, there is a present-day mass function that is top-heavy in nature. And the distribution of the stars doesn't reflect the expectation of dynamical relaxations of stars in the regions. You will expect actually the low mass stars to be distributed according to a cusp-like density profile. It's a theoretical result that goes back to Wolf and Bacall. And instead, you see that the massive stars are they sort of show like a cusp-like distribution, and the low mass stars don't, which is opposite to what you would expect, because low mass stars live longer. And so they had more time to relax, and the young star don't, the massive star don't. And so, you know, it's clear that something had happened there that created a special distribution and population of stars. There's also observation of disk of stars aligned, aligned disk of stars in the inner regions that are puzzling. U11 has worked on this in the past and trying to understand, you know, are these stars formed there? And so I think there, to me, that's a right place to try to connect this type of astrophysics with the observations. And, you know, ideally, we want to make predictions that can be compared to the inner region of the galactic center and see if we can reproduce some of this interesting stellar population. And to get there, we still need to build our framework, in the sense that we have the stellar evolution, but now we know we need to add a better understanding of AGN disks and also a better understanding of the dynamics. So that's why, you know, this is a little bit of a multidisciplinary astrophysical effort. But we have a lot of people in the New York area that are helping, and then I think there will be some interesting progress coming along.
Very cool. Very cool. So,
Yeah.
one, I want to thank you very much for taking the time to walk through your very lovely article there. And number two, given how you ended there, it seems like a very rich field to go over the next 5 years. We're going to have some new observations. There's obviously some, you know, more refined calculations that can be done, both with the framework you developed and otherwise. So I think you sort of answered the question there before I asked it of, you know, where do we go over the next 5 years? And I think you hit that well.
Yeah. There's other things that we thought about that I think would be interesting in the context of some of the new missions coming online. For example, in this region, if the stars exist and they explode, if they're all massive, then maybe the variability that we observe in AGN could be partly due to stellar explosion and not just to accretion on the supermassive black hole. And in that sense, you know, you know, the Vera Rubin Observatory is going to be the to-go instrument to try to see if this type of variability can be explained just with our understanding of accretion process on a supermassive black hole, or it requires also stars going off here and there. And some people already started doing this with ZTF. So I think there is interesting connection also with new probes that are coming online.
Very cool. Crack open that whole field. Very nice. Very nice. All right, everyone, that'll do. Thank you so much, and we will see you on the next one. Bye-bye.